Part 2 of our equilibrium ionizations, looking at weak bases and polyprotic acids. Now, up until this point, we've had all of our discussions focused on weak acids. Weak bases will also ionize via an equilibrium process the same way that a weak acid will. For instance, ammonia will ionize in water to form ammonium, NH4+, and hydroxide. Most weak bases are not soluble in water. Most of the soluble weak bases that we will see are either ammonia or derivatives of ammonia, which are called amines. These are functionalities where hydrogens in the ammonia molecule have been replaced by something else. For example, a CH3 group or two CH3 groups, so NCH3 H, NCH3 NC2H5 3, things like this, which have these carbon derivatives on the nitrogen. The nitrogen becomes more basic as the carbon replaces hydrogen on the nitrogen. So these amine derivatives are actually stronger bases than NH3 is. We can relate the behavior of an amine through the NH3. We calculate what's called a Kb, or a base dissociation constant. The Kb value for the above equilibrium expression, because water is an activity of 1 and doesn't appear in the equilibrium process, will be concentration of NH4+ times concentration of OH- over concentration of NH3. This happens to come out to 1.8 times 10 to the minus 5. Interestingly, this 1.8 times 10 to the minus 5 is the same value, so the Kb for NH3, as the Ka for acetic acid is. They're equal in their magnitude. However, this is simply coincidental. There is nothing chemically related to this. It's just something that happens to be. The only information that we can get from that relationship then is that an ionization for ammonia and acetic acid of equal concentrations will be equal ionized. So for example, if we wanted to calculate the concentrations of all the species and determine the pH for a 0.2 molar solution of ammonia with a Kb value of 1.8 times 10 to the minus 5, we would first write out our equilibrium reaction. The initial concentrations are 0.2 for NH3, 1 for water, approximately 0 for hydroxide, and 0 for ammonium. Change will be minus x to the ammonia and plus x to the hydroxide and the ammonium. The overall equilibrium then will be 0.2 minus x for ammonia and x for hydroxide and ammonium, same as it's been the whole time. Plugging this into our Kb expression then, our Kb is 1.8 times 10 to the minus 5 is equal to x times x divided by 0.2 minus x. Because 1.8 times 10 to the minus 5 is a relatively small value, we can make the assumption that x is negligible, predicated on the same idea that it has to be within 5% of 0.2 molar. So solving for x, ignoring the minus x in the bottom, our x value is equal to 0.2 times 1.8 times 10 to the minus 5 as a square root. This gives us 1.9 times 10 to the minus 3 as our hydroxide concentration. 1.9 times 10 to the minus 3 divided by 0.2 as a percentage is only 0.95%, which holds our assumption valid. Hydronium will be equal to the Kw value divided by the concentration of hydroxide. So 1 times 10 to the minus 14 divided by 1.9 times 10 to the minus 3 gives us a hydronium concentration of 5.26 times 10 to the minus 12. The hydronium concentration then, at 5.26 times 10 to the minus 12, the ammonium concentration equal to the hydroxide concentration at 1.9 times 10 to the minus 3, and the ammonia concentration still at 0.2 molar because most of it doesn't ionize. To find the pH, we would take the negative log of the hydronium concentration, giving us a pH of 11.28. We have similar assumptions for a weak base that we do for a weak acid then. We assume that the concentration of ammonia stays the same as the solution concentration, the concentration of the hydroxide being equal to the concentration of the ammonium. So both of our dissolved species will be equal in concentration, and the parent species NH3 is assumed to not change to any great degree in its concentration. Now Ka for polyprotic acids is different from Ka for monoprotic acids. All of our discussion so far on acids and bases has been monoprotic, or single functionality. Now we're looking at a polyprotic system where we have more than one hydrogen potentially ionizing. Polyprotic acids, because they have more than one hydrogen, have more than one Ka value. Each hydrogen has its own Ka value. For instance, phosphoric acid, H3PO4, undergoes three different ionization processes. The initial ionization removes one H, making H2PO4 minus, with a Ka value that reflects H3O plus, H2PO4 minus, divided by H3PO4. This has a Ka of 7.5 times 10 to the minus 3. That H2PO4 minus can then undergo further ionization, forming HPO4 2 minus, with a Ka value of 6.2 times 10 to the minus 8. That HPO4 2 minus can undergo one more ionization, producing PO4 3 minus, with a Ka value of 3.6 times 10 to the minus 13. We note that the Ka value progressively shrinks, moving down the series from H3PO4 to H2PO4 minus to HPO4 2 minus as our reactive species. Ionization, therefore, must be more difficult going sequentially down this system. This intuitively makes sense because removing an H plus as a positive ion from an anionic substance would be more difficult. I'm trying to pull something positive off of something that is negative, which is more difficult than pulling something positive off of something that is neutral. We see the same trend in ionization energies for second and third ionization energies of ions. So successive ionization constants often will decrease by a factor of 10 to the 4 or 10 to the 6 from the previous constant. So calculate the concentrations of all species and determine the pH for a 0.1 molar solution of phosphoric acid. We write out our equilibrium reaction. Our initial concentration of phosphoric acid is 0.1 for H2PO4 minus, 0, and for H3O plus 0. Our changes are minus x, and plus x respectively. So looking at our equilibrium expression, we plug this into the equilibrium expression, giving us 7.5 times 10 to the minus 3 times x is equal to x times x divided by 0.1 minus x. Because 7.5 times 10 to the minus 3 is a fairly large small number, it is less than 1, but it's pretty big compared to some of the others that we've seen, it's likely that it's going to be too large. We try the assumption anyway, but we will have to go to our secondary method if it fails. Solving for x then, assuming that the x in our 0.1 minus x is negligible, our x value is 2.7 times 10 to the minus 2. If I compare that as a percentage against 0.1, it is 27% of 0.1. We are limited to 5% of 0.1, which means that this assumption is now invalid. Because the assumption fails, we have to move on to solving the quadratic equation. The quadratic equation is x squared plus 7.5 times 10 to the minus 3x minus 7.5 times 10 to the minus 4 equals 0. If I plug this into my quadratic formula, I'll get x values of negative 0.0314 and 0.239. I pick the positive value because I can't have a negative concentration. So our hydronium concentration is 0.024 molar. Our H2PO4 is the same at 0.024 molar. If I subtract 0.024 molar from 0.1, I get a phosphoric acid concentration of 0.076 molar. And my hydroxide concentration coming from Kw divided by 0.024 is 4.2 times 10 to the minus 13. Moving on to the next ionization, H2PO4 minus ionizing to HPO4 2 minus. We have an initial concentration of 0.024 for H2PO4 minus that we just calculated in the previous step, and an initial concentration of H3O plus at the same 0.024. Our changes are still minus x, and plus x. This gives us an equilibrium expression, which has x times x plus 0.024 divided by 0.024 minus x. This all equals a Ka value now of 6.2 times 10 to the minus 8. Now 6.2 times 10 to the minus 8 is a small number, so it's likely that our assumption that x is negligible in the addition and subtraction steps will be valid. If we make that assumption, solving for x, 6.2 times 10 to the minus 8 is equal to x times 0.024 divided by 0.024. So x is 6.2 times 10 to the minus 8. Comparing that as a percentage against 0.024, we find that it is 2.6 times 10 to the minus 4%. That is extremely small, 0.00026%. Our hydronium concentration then is still 0.024 because if I were to add that to 2.6 times 10 to the minus 4, it's going to be negligible. Our H2PO4 concentration is also unchanged. Our HPO42- concentration is our 6.2 times 10 to the minus 8. And our OH- concentration is our same 0.024 divided into 1 times 10 to the minus 14. Moving on to the final step, calculating the concentration of PO43-, the final ionization stage. HPO42- ionizing to PO43-. Initial concentration is 6.2 times 10 to the minus 8 for the HPO42- and 0.024 for the hydronium. We have the same changes as before, giving us equilibrium expression. Plugging that in, 3.6 times 10 to the minus 13, the new Ka for this process, is equal to x times x plus 0.024 divided by 6.2 times 10 to the minus 8 minus x. Once again, this is an even smaller number, so we can assume that x is negligible. Solving for x as assuming x is negligible in our addition and subtraction steps, we have 3.6 times 10 to the minus 13 equals x times 0.024 divided by 6.2 times 10 to the minus 8. X is then 9.3 times 10 to the negative 19. Comparing that against 6.2 times 10 to the minus 8 gives us a value of 1.5 times 10 to the minus 9%. So this is extremely small. Our hydronium concentration is still the same, 0.024. Our HPO42- concentration is 6.2 times 10 to the minus 8, still unchanged. Our PO43- concentration is 9.3 times 10 to the minus 19, and our hydroxide concentration remains unchanged. If we sum the steps for H3O plus concentration, 0.024 plus 6.2 times 10 to the minus 8 plus 9.3 times 10 to the minus 19, gives us this long number. The first non-zero digit after the 4 is 5 decimal places past it, which means rounding to any sort of reasonable significance, we ignore the addition of the second 2 amounts of hydronium. So we can assume that the hydronium concentration is 0.024. Our assumption of the small x value holds true. Calculating a pH by taking the negative log of 0.024, we get a pH of 1.62.